Week 8, problem 4. For a research project, a student needs a solenoid that produces an interior magnetic field of 0.03 teslas. She decides to use a current of 1 amp and a wire of 0.5 millimeters in diameter. She winds the solenoid in layers on an insulating form 1.0 centimeters in diameter and 20 centimeters long. Determine the number of layers wire needed. Round your answer to the nearest integer. Alright, so I think the trouble with this guy is just going to be figuring out what they're saying. So, we're going to start this off by drawing a picture. So, make a circle, circle, oh, circle. That's reasonable. I'm good with that. I will copy, paste, and this will probably make it more confusing. Maybe. We'll see. Maybe if I do then erase. Now I'm getting overly complicated. You're not erasing, are you? That's okay. Doesn't matter. Oh, nope. Then we'll go to lines. No, I don't want to go from there. Oh, straight up and down. There we go. Something like that. Copy, paste. There we go. Alright. So now we got our picture. This is the form that we have that she's using. And we're told that the form is 1 centimeter in diameter and 20 centimeters long. So basically not drawing a scale in any conceivable way. Got blue. So this guy will be 0.2 meters. And that guy right there will be an insulating from 1, so this will be 0.5 centimeters. 0.5 times 10 to the negative second meters. Okay, so what's then going to happen is we need to find the number of layers that she needs. So by layers, so there's going to be a bunch of coils like this. So this is going to go, say, like this, and we'll say it has a magnetic field going upward, which means that it's going to go in here, out here, and this should basically be considered one layer. And if we need another layer, we'll put it on over here. And so when they ask how many layers do we need, it's how many of these guys do we need. So she decides, she winds, insulating, and we know that the wire itself is 0.5 millimeters. So this is this distance right here is 5 times 10 to the negative 4th meters. Got it. Alright. So round your answer to the nearest integer. Determine the number of layers of wire needed. Okay, so we're going to start with the formula for a solenoid. So the formula for a magnetic solenoid, which I'm pretty sure is the only type of solenoid that really exists. You not I number of turns per length. Okay. So first I'm going to find out is how many turns we have down here. So this is going to be, let's see, each piece of wire has a diameter of 0.5 millimeters. Okay, 5 times 10 to the negative 4th, and this is 0.2 meters. So if we do 0.2 meters divided by 5 times 10 to the negative 4th meters. Alright, this is 2 times 10 to the negative 1. This gives us, I'm just going to Wolfram it. 0.2 divided by quantity 5 times 10 to the negative 4th. 400. Gosh, that's a lot. That seems reasonable. Let's see if I can do the math real quick. So this would be like 20 times 10 to the negative first. 2 times 10 to the negative 1. 20 times 10 to the negative second. Yeah. Over 5 times 10 to the negative fourth. Cancel these guys out. I get 10 squared. This is 4. That's 400. Yes. I believe Wolfram is correct. Well done, Wolfram. Never let me down. And the few times you have, it's probably actually me who was wrong and you were right. So we have 400 going down this direction. Okay? So we're going to have, this is going to be 4 pi times 10 to the negative 7th times I, which is 1 amp, times n, which I'm going to call 400 over length, which is 0.2 meters. And so basically we're going to have 400 of those guys for every layer. And we're going to find out what magnetic field one layer gives us. So figuring this out, so we can do, this will be 10 to the negative 5th, which is 4, change this to a 2, change that to a 0.1. Yeah. And divided by 0.1 is the same as multiplying by 10, which is the same as 10 to the negative 4th, which is 4 pi times 10. Now, 8 pi. 4 pi times 2 is 8 pi times 10 to the negative 4th. 8 pi times 10 to the negative 4th. I could probably simplify that more. I don't care to. So 2.5 times 10 to the negative 3rd. Equals 2.5 times 10 to the negative 3rd Teslas. Alright, and what does she want? She wants a 3 times 10 to the negative 3rd. So she wants a 3 times 10 to the negative 2nd. 10 to the negative 2nd Teslas. So we need 3 times 10 to the negative 2nd, and each layer gives us 2.5 times 10 to the negative 3rd. I do this 2.5 times 10 to the negative 3rd Teslas per layer. Alright, per layer up here. Cancel the Teslas. And I'm going to do 3 times 10 to the negative 2nd. 3 times 10 to the negative 2nd divided by the answer I just got. That should give me a number like, what, 10? 12. So I'm going to call that 12. Equals 12 layers. So what this is saying then is we're going to need 12 layers of wire. So these are extended just a little bit more. There we go. So right here we have 12 layers. All right. So determine the number of layers of wire needed. Bam, we just did that. 12. Round your answer up, then you're saying, it makes sense. Because she wants at least the 0.03 Teslas. So 12 layers doesn't seem all that bad. Yep. Alright, so determine the total length of wire. Use the integer number of layers in the average layer diameter. Okay. So we have the integer number of layers, 12. We're going to say we have 12 layers. So the idea is each layer is going to have more and more on it. So if you think of it like this as a roll of paper towels, the paper towels on the outside is going to have a larger circumference, and you're going to have more paper towels per layer on the outside than layers on the than towels per layer on the inside. So what we're going to do here is we're just going to take the average. It's not a good way of doing it, but it's an easier and close enough way of doing it. And they told us to do it, so we're going to go that way. So I'm going to say that the average diameter, so I'm going to say the average diameter, we want to find out what this guy is. I'm going to say that the inner diameter, so to find the average, we're going to add the 2 and divide by 2. It's going to be right here, 0.5 times 10 to the negative second. 0.5 times 10 to the negative second. Plus, and then the outer diameter is going to be 0.5 times 10 to the negative second, plus 12, which is the number of layers, plus the diameter of each of the wires, which is 0.5 times 10 to the negative third, which is 5 times 10 to the negative fourth. So what I'm doing here is I'm finding this diameter right here, and then this diameter right here. So this right here is diameter big, and this guy will be diameter small. That seems reasonable. Yep, and then we're going to divide by 2. So I'm going to find out what the second part is. So we're going to do 5 times 10 to the negative second plus 12 times 5 times 10 to the negative fourth. 0.056. So this guy is probably 0.6, that guy's 0.05, 0.056. So we have 0.05 plus 0.056 divided by 2. I'm not even going to do any math there. It's going to be like, maybe about 0.053 meters, which is 5.3 times 10 to the negative second. So that's what I'm going to use for the average diameter. So, and then that's going to be the average diameter. Oh, those are radii. I'm using radii. That's okay. I can totally use radius here. I'm pretty sure I can. Yeah, because we have to use these are diameters of wire here, but each of these diameters are contributing to the radius. Yeah, I'm totally good with this. But I am going to cross this guy out and be like, radius. There we go. That makes sense. Yeah, we got this. Bam, go team. Confidence. Wonder if confidence really works with math. Okay, so now this is our radius for if we have a circle of wire going around like this. Oh, didn't mean to click. Oh no, didn't mean to click there. Around like this. That's what's going to be the average radius of that wire, which will be related to the average layer diameter, which makes sense because between this and that. Okay, so now, I'm going to do a circumference of one loop of wire. So one loop is be 2 pi r, which equals 5.3 times 10 to the negative second times 2 times pi. So I'm going to do 5.3 times 10 to the negative second times 2 times pi. And this gives us 0.333. 0.333 meters. That's pretty good. Okay, I'm good with that. So that's like 0.05 times 6. Yeah. Alright, let's go with that. So then we're going to have, like, if you look at this, it's kind of like a square. We're going to have 400 deep, 1200 wide. No, 400 deep, and then, or 12 deep, 400 long. So if I do 0.333 times 12 times 400, that'll give us a total length of the wire, which might actually be pretty big, times 12 times 400. Bum 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 bum. Holy fudge. That's like a kilometer of wire. Now I'm starting to question myself. Well, I'm going to write that answer down and just see where it goes. 1598. Alright, I see my problem here. So right here, I did 0.5 times 10 to the negative second, and it's like, bam, 0.05. Nope, it's supposed to be 0.005. When I carry all the way all the way through, so I do extra 0, extra 0, extra 0, make that a negative 3, make that guy negative 3, put a little 0 in there, do a little 0 in there. And what I get then is 159.8. 159.8 meters. Alright, so before I wrap this guy up, one other thing that I'm not quite sure how they count things, but just in case. So here I counted it from this inside of the diameter here. I called this the inner diameter and this the outer diameter. So what they might want you to do is count it from, so what I did was I counted from, let's see here, like this for the top and that for the bottom. Well, one other way to do it would be, and let's do pink, would be to count it from the center. How big a difference is that going to make? I don't know. Probably not a lot. But I'm going to recalculate it again that way too, just in case. So this is the way using the bigger, the full diameters. This is using the diameters from the actual centers of each individual wire. So this then would be, let's see, where can I get this in? Oop, I'm going to copy this guy just so I can use the same format. So average diameter, nope, we're going to go radius. Average radius, and instead of using 0.5 times 10 to the negative second, I use 5 times 10 to the negative third, and then I'm going to add on to that half of one wire, plus 5 times 10 to the negative fourth over 2, because that's going to the center of the wire, plus, and then we're going to do 5 times 10 to the negative third, plus, and since there's 12 layers, this I would have had to go out to the outside of the line anyway, so I should have had, instead of 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. So I'm actually going to draw this out just to make sure I know what I'm doing here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Alright. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 works. But here I'm going to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm going to do 11.5. 6, 7, 8, 9, 10, 11. So, plus, change this guy back to pink. There we go. We're going to have 11.5. And finer tip. There we go. Times 5 times 10 to the negative fourth. And that extra 0.5 is just going to make it so we're at the center of the last wire. And then we'll divide by 2. Alright. So this is probably going to be obnoxious to enter, but maybe worthwhile. I'm going to try this. 5.3 times 10 to the negative third. See, that was my previous error. Plus 0.5 times 5 times 10 to the negative fourth. parentheses, parentheses, plus, I'm just going to copy this guy real quick. Copy, paste, and I'm going to change the 0 to an 11. Yeah, 5.3 times 10 to the negative third. That's supposed to be a negative. Hop. And 11.5. Yeah, we're probably good on that. Divided by 2. So now we get 0.0083. That's quite different than 0.056. Interesting. I'm going to go with that. So 0.0083, which equals 0. I'm going to call this 8.3 times 10 to the negative second. So 8.3, no, negative third, almost got me again. 0.83 times 10 to the negative third will be the radius. All right, so we got the average radius. So average circumference will be 2 pi r squared. 2 pi times 8.3 squared times 10 to the negative third squared equals. So now we have 8.3 times 10 to the negative third squared times pi. Did I have a 2 in there? No, I shouldn't have that 2. Just pi r squared. No, nope, it's 2 pi r. All sorts of mistakes. Bush league. Oh, times 2 times pi. All right, 2 pi r. Bam, and we get 0.052 equals point. Put in a 2. Put an extra 2 in there. Negative second. That's the average circumference of loop. Alright, and then we take that and we multiply it by the, see, what did we get first time? 5.3? Yeah, 5.2, 5.23, maybe. Alright, then we take this number, multiply this by 12 by 400, and then we're going to get 250. Whoa, that's a reasonably big difference. Okay, I think that's about right. 250 meters. Therefore, so here we're going to have total equals 5.2 times 10 to the negative second times, we said 12 layers times 12 times 400. So these cancel, and we get 12 times 12 times 4, which is about, I don't know, 50. 50 times 5.2, we'll call that about 250.3. So this, I believe, is the right way to do it. So do it the way I did the second time, not the way I did the first time, which was kind of sketchy. Nah, not kind of sketchy. It was misguided, youthful exuberance. So I think that's the trick on how to do this guy. So backing up a little bit just to look at it. Let's get rid of this. Whoop. 250. So the idea here, backing up, is you want to create an electromagnet. To create this electromagnet, you know how much current you're going to use, and you know the type of wire you're going to use. You also know the form you're going to use. So you're going to wind a whole bunch of wires up and down here. So you know you have 20 centimeters. 20 centimeters. Each wire is 0.5 millimeters, which means you're going to get 10. You're going to get 10, 20. I think you're going to get 20 pieces of wire for every centimeter, and then you do the whole 20 centimeters. You're going to get a total of 400 wires, circle loops of wire up and down. And then after you do one loop all the way down, you're then going to put on a layer. And the layer, so then you find the magnetic field from one layer, and then you keep adding on more layers until you have the total magnetic field that you want. After that, you then basically have to use geometry to figure out, alright, this is going to be the radius of the inner wire. This is going to be the inner radius of the last wire, because you have to measure from the inside of the wire. You then use that to find the circumference of each wire, of each loop of wire, and then you find the average, use the average radius, and then you multiply it by 400 wires up and down, and then 12 sets of wires left and right. Alright, and that is how you do this problem. Got it? Alright, see you on problem 5.